This is a short video to explain matrix multiplication in lab 4. Now, if you are not familiar with matrices, they are written like a two-dimensional array of elements. So, for example, this is a matrix 1, 3, 5, 4, 5, 2. So, this matrix has two rows. This is row 1 and row 2 and 3 columns, as you can see, and as a result it has 3 times 2 equal to 6 elements in total. Now, one of the things that occurs quite often in scientific computation is that you have to multiply two such matrices and get a third matrix, and it's usually a very quite a compute intensive task because many scientific applications require you to multiply many matrices and very large matrices. For example, there are applications where you have to multiply a million by million matrices where there are 1 million rows and 1 million columns, for example. Now, what is the procedure for multiplying such matrices? The procedure, first of all, we have to know that we can multiply only certain matrices and not all matrices. In other words, given two arbitrary matrices, we may not be able to multiply them. The multiplication may be undefined. So when is the multiplication defined? The multiplication is defined in the following case. So suppose this is a matrix A and it's an m cross n matrix. In other words, there are m rows and n columns. For example, if you have 3 rows, then m equal to 3, and if you have 3 columns, then n equal to 3. So in that case, A will become a 3 by 3 matrix. Now, it is possible to multiply two matrices when I can show you. I can write another matrix here, which is B. And the B matrix, if the number of columns of the A matrix matches the number of rows of the B matrix. In other words, B must be an n cross P matrix. In other words, the number of columns here is equal to the number of rows here. So it could be n rows where n is some number which is equal to this n, and p columns where p is another integer. Now, how do you multiply these matrices? I'll show you first with an example, small example, 3 by 3 matrices, how to multiply them. So suppose I have a matrix 3, 3, 2, 1, 0, 1, 2, 1, 0, something like that. And this is a 3 by 3 matrix. I'll write as a special case another 3 by 3 matrix. Let us say 1, 0, 1, 0, 1, 1, 1, 1, 0. So this is a 3 by 3 matrix again. As you can see, the number of rows here is equal to number of columns here, and hence the multiplication is defined. So the way the multiplication is done is to take the first row of the matrix here, the A matrix. Let us call this A and this B. So first row of A matrix and the first column of the B matrix, and form what is the dot product. In other words, we multiply the elements which are corresponding. So for example, this element here with this element plus this element here with this element plus this element here, multiply that with this element. In other words, if I write 3 times 1 plus 3 times 0 plus 2 times 1. You can see I am multiplying the corresponding elements here. 3 times 1 plus 3 times 0 plus 2 times 1. So what is this number? This is simply, this thing is 0, so this is 3 plus 2 equal to 5. Now 5 becomes the first element of this new result matrix. To get the next element here, I have to multiply this row with this column in the same way. And if I, without going into the details, if I multiply 3 times 0 is 0, 3 times 1 is 3, 2 times 1 is 2. So I add them up and I get 5. Similarly, the third element here, here is obtained by multiplying this row with this column. So 3 times 1 is 3, 3 times 1 is 3, 3 plus 3 is 6. So that's how I get the first row of the result matrix. To get the second row, I have to repeat this with this row of the A matrix and multiply that first with this column, then with this column, and then at the end with this column. So you can see it is a repetitive process, and I am not doing the complete multiplication. Perhaps you got the idea already. And one of the nice things about this algorithm, the way two matrices are multiplied, is that it's highly parallel. For example, when, first of all, you see when I am getting this particular row, in other words, I'm multiplying this row here with all these three columns, I can at the same time obtain the next row here by multiplying this row here with all these three columns. There is no dependency. They are completely independent computations. So obviously, this is a very good candidate for parallelizing with OpenMP. Even within that, I mean, when I am multiplying, I just told you about a high-level parallelism, that every row of this result matrix can be obtained in parallel. But even each element within a row can be computed in parallel. For example, when I was multiplying this row with this column, at the same time, I can multiply the same row with the second column. There is no problem because they are completely independent and they can be computed at the same time. So you can see there is another level, another finer level of parallelism as well. And finally, when you are multiplying just this row with this column, you can do the multiplication of this element with this element. At the same time, you can do the multiplication of this element with this element. So there is a third level of parallelism. So matrix multiplication is really a highly parallel procedure. Now what I'm asking you to do is to implement this matrix multiplication in OpenMP. And for that, first of all, you have to write a sequential program. Now, as I have shown you, the way to multiply two matrices, basically the sequential program will be 3 nested for loops. Why? Because if you remember the picture, we multiplied like this. This row was multiplied by this column, so that we get one element, and that is the innermost for loop. Then, okay, I write the result here. So an element of the result matrix will be computed by the innermost for loop. A row of the result matrix will be computed by the next level for loop, and then all the rows will be computed. My usual problem. So all the rows will be computed by this outermost for loop. So I'm not giving you any more hints, and of course there are millions of implementations of matrix multiplication on the web, so perhaps you can look it up. However, I would suggest that you try to work out the logic on your own and write first a sequential program for matrix multiplication. I have given some instructions how to create these matrices by generating random numbers, and then starting from your sequential program, you can parallelize your program using OpenMP and do some performance evaluation. Okay, that's the main task in the lab, fourth lab.